Hello everyone, my name is Eric Larson and I'm an artist in Vancouver, Canada, and this is my video submission to this contest, the Summer of Math Exposition. What I'm going to be doing in this video is introducing you to the geometry of the circle from a base 12 perspective. So we're going to be doing some base 12 math, some base 12 geometry, and basically what I'm doing is sharing with you some discoveries that I've made in base 12. It's a subject that I've been exploring for the past 5 years or so. I feel like I've made some significant discoveries, and this video is me sharing those discoveries with you. I do have a YouTube channel called Duodecimal Division, and on that channel there's about 12 videos, all of them roughly 10-15 minutes in length, where I explain all this information. What I'm going to be doing in this video, the best I can, is to present all that information in one video, condensing it down, sharing it with you in as concise a way as possible. It is a little bit low tech. It's just going to be me using blank paper, graph paper, pen, pencil, ruler, compass, straight edge, that kind of thing. But I really got from the video explaining this contest that content is king. So I've got some really good content, I believe. What I'm going to be doing first is sharing with you what the really significant difference is between base 10 and base 12. Then I'm going to share with you a geometric pattern that we have missed in base 10 that really comes into focus in base 12. We're going to do a little bit of comparison between base 10 and base 12 in regard to this pattern so you really understand the difference. And then we're going to use that pattern to create a diagram that generates all 360 degrees. So just to be really clear, what I'm going to be doing is showing you how to divide the circle into 360 equal parts using this pattern that only really exists in base 12 geometry. And then at the end of the video, I'm going to go over the implications of the diagram that I will share with you. I don't want to get into that right now. I kind of want to leave it for a surprise, but it does have to do with the circumference of the circle in relation to its diameter. So a lot of ground to cover. So here we go. What is the real significance between the differences between base 10 and base 12 geometry? All right, so usually when we think of base 10 and base 12 and are comparing the two, we're talking about counting in groups of 10 or in groups of 12. So if we were to say approach a barrel of apples and we were to count the apples from a base 10 perspective, we say we come up with 81 apples in total in the barrel. Now someone who was to approach that same barrel of apples from a base 12 perspective would come up with 69 apples. They would have 6 groups of 12 with 9 apples left over. So we can see that ultimately, even though it seems like we got two different numbers, the number of apples in the barrel is still the same. So it seems like it doesn't really make a difference between the way we count. It's still the same amount of apples in the barrel. But the real difference isn't so much in the counting in groups of 10 or 12, it's in the dividing up of the 1. If we were to pull an apple out of the barrel and divide it up from a base 10 perspective, we would have 10 pieces of apple. From a base 12 perspective, we would have 12 pieces of apple. And if we were to compare those two pieces, one from base 10, one from base 12, we would see that the base 12 piece is a smaller piece of apple. So if we take that idea and apply it to lengths, we can see that 0.1 in base 10 is a longer unit than 0.1 in base 12. So when we apply that to the Cartesian plane, we're going to find that we have a denser grid in base 12 than we do in base 10. All right, so here we have a piece of paper with a very large square drawn on it, and I've divided it into half. Here's the half line here. The top half has been divided into tenths and the bottom into 12. So this is a base 10 version of dividing up the square. This is a base 12 version of dividing up the square. So that's pretty straightforward. Halfway is 0.5, and down here we can see that halfway is 0.6 in base 12, and that the only lattice point that really is shared by both sides is the center point of the entire square. And so here you can see that as I go 0.8, 0.9, point A, and then point B, obviously we need 2 extra numerals to represent the 2 extra numbers in base 12. And so I'm going to be using capital A and capital B to denote those 2 numbers. All right, so we're going to look at another example. We're going to put those 2 on top just to really make sure we understand the difference between base 10 and base 12 as it applies to the Cartesian plane. Okay, so here we have that same size square, and I've just put those two different grids on top of each other. We have base 10 in red and base 12 in black. So again, you can see that, this point here has the same coordinates. We're going up 1, so the x is 0, the y is 1. Over here, 0.51 for the red point, but 0.61 for the black point, black coordinate. Again, the only point that they share is the center, and all the rest of the lattice points line up differently. So of course, this isn't just in relation to going along the horizontal and vertical lines, but any type of decimal version of any number is going to be an actual different sized unit. So for example, the square root of 2 in base 10, we have a larger version of 0.1 root 2 than we would in base 12. 0.1 root 2 is going to be a smaller sized unit. Okay, so that's the basic difference. It's not that complex, but it has significant implications. So now what I'm going to do is show you the geometric pattern that I discovered. I'm going to just show it to you without any base. We can take a look there, and then we'll again compare the base 10 and base 12 versions. Okay, so here's the geometric pattern that I've been talking about. You can see that it's a type of dodecagon that repeats itself. And what makes this pattern very powerful is that all of the points that define this shape are actual lattice points. So all of these points are lattice points on this grid, and at this point we haven't actually defined the base of the grid. So if we look at these individual squares as decimal places, we're going 0.1, 0.2, 0.3. We haven't decided where the 1 is going to be. So what I'm going to do now is look at this pattern from the perspective of base 10 and then from base 12. And so I do want to point out that because I'm using graph paper, it's going to seem like I'm making the 1 bigger. For base 10, there's going to be 10 little squares, and base 12, there's 12 little squares, so that the 1 will seem bigger. But again, I really want to emphasize the fact that ultimately the 1 is the same size, and the little squares are bigger in base 10, again, in relation to the 1 than in base 12. So just a little bit of back and forth there. I really want to make sure you understand that there is a difference. You're going to see the difference anyway, but it's going to be a little bit perhaps misleading because we're keeping our decimal the same size in this example. And again, that's simply because I'm using graph paper and I'm not adjusting the size of the decimal place from one example to the other. Okay, so here we're going to look at the base 10 version, or the relationship of this pattern to a base 10 grid. Okay, so here's that exact same pattern on a base 10 grid. What I've done also is drawn a circle on the inside here with the radius of 1, so we can see what the relationship of that circle is to this pattern. You can see that there's actually 0.3 is the distance on the x-axis between the circumference of the circle, its edge, and the first point here in this pattern of the dodecagon. So we can see where the points line up in relation to the grid beneath. Basically, that's what the pattern looks like on a base 10 grid. So that's always where it's sat in terms of our geometry, our base 10 geometry, and basically that's what it looks like. So we're just going to skip now to the base 12 version and see what the difference is between these two bases in relation to this pattern. Okay, and so here is that same dodecagon pattern on a base 12 grid. So you can see right away that its relationship to a circle with the radius of 1 is a little bit different. That circle comes closer to the inner dodecagon, and the distance between the edge of the circle or its circumference and this first point here is just now 0.1. So again, the 1 hasn't gotten larger. It's just the relationship or the ratio between that circle and the dodecagon is different. Things line up differently. And the defining points of the dodecagon are now landing on the 1, 2, 3 on the x-axis and the 1, 2, 3, 4, etc. on the y-axis. We can see how well that dodecagon fits on the base 12 grid. So the slope of this line here, of these lines, you go over 1 and up 0.7, over 1 and up 0.7. That's the slope of that line. And because it's landing on the 1, we can see how incredibly basically solidly it's planted. No matter what number we go over on the x-axis, we're always going to have a corresponding 0.7 or 0.07 on the y-axis. So there's always going to be those 2 points landing, and this line is always going to be present on the grid no matter where we are. So we're going to go over that more deeply now. We're going to look at the geometry of the very first dodecagon. We're going to start to analyze the lengths and the slope a little bit more and just see what the significance is of this pattern, and we're going to do it from a base 12 perspective. Okay, so here is the dodecagon again on a base 12 grid, and this is a much larger scale, as you can see. And so this is the very first inner dodecagon in that pattern. And what we're going to do now is look at the lengths of the dodecagon and just make sure that all of the lengths are indeed the same length, they're all the same size. So I'll start by drawing a triangle up here, a little right angle triangle, and the lengths of these sides are 0.5 in length, 0.5 and 0.5, and so the length of this side here is 0.5 root 2. So now we're going to look at this long triangle here, just delineate it for us. So again, it's a right angle. This length here is 0.1. And this length here, right over here, is 0.7. So we're going to use the Pythagorean theorem. We're going to square 0.7. So 0.7 squared equals 0.41. This is our first foray into some base 12 math. And of course, you can convert back and forth or just test that to 0.4 times 12. 4 times 12 is 48, plus 1 is 49. So that's the base 12 version, or the base 10 version. So 0.7 is the square root of 0.41. And so 0.1 squared is still the familiar 0.01. So 0.41 plus 0.01 equals 0.42. A squared plus b squared equals c squared. So c squared equals 0.42. So here our c equals the square root of 0.42. So is 0.5 root 2 the same as the square root of 0.42? Well, let's just go over here and see what 0.5 squared is, and it happens to be 0.21. Again, it's two groups of 12 and 1 if you just want to convert, compare back and forth. So 0.5 root 2 is the square root of 0.21 multiplied by the square root of 2, and we can see that that does indeed result in the square root of 0.42. So we can see that both the sides, and indeed all of the sides of this dodecagon, are equal length, and they are the length of 0.5 root 2. All right, so now what we're going to do is look at the slope of this line here. So I'm just going to kind of go on top of that. We're going to look at the slope of that line, or the length, I should say, of this line. It's basically the dimensions of this triangle here that's formed by those points. So we know that that bottom length here is just the length of 1, and we know that this length here is 0.7, or the square root of 0.41. So this length here becomes the length of 1, or the square root of 1.41. Again, applying the Pythagorean theorem. So now what we want to do is look at the angle of that line, or the slope, and compare it to the special right angle triangle, or the 30-degree angle, the 30-degree line, and just see what the relationship is between the slope of this line here and the 30-degree line. I just do want to point out for this video, I'm going to be referring to the 30 degree, 45, 60, 90 degrees in their base 10 version, although we are in base 12, and once we kind of go farther into base 12, 30 degrees turns into 26 degrees, and it's a little bit different, but just for ease of communication, again, I'm going to be referring to the angle in their base 10 versions. Okay, so now we're going to compare again the slope of these lines, or that triangle, to a special right angle triangle. Okay, so here at the top we have the dimensions of the special right angle triangle, where we have the right angle on either side. We have the 1 and the square root of 3, and then the hypotenuse is the square root of 4, which is the same as 2. So here we have the triangle that we were just looking at, where we have the base of 1, and the other side of the right angle is 0.7, which is the same as the square root of 0.41, and the hypotenuse is the square root of 1.41. So we want to find out what is the dimensions of a right angle triangle when the base is 1, so we can compare the two. So in order to make that base 1, we're going to have to divide by the square root of 3, which means we're going to have to divide all the sides by the square root of 3. So square root of 3 divided by square root of 3 is 1. So 1 divided by square root of 3, or the square root of 1 divided by the square root of 3, results in the square root of 0.4, because 1 divided by 3 in base 12 is 0.4, and that gives this side here 4 divided by 3 in base 12 equals 1.4. So the square root of 1.4 is the length of this side. So when we look at this triangle and we look at this triangle, we can see that this side here is a little bit longer. Here it's a square root of 0.41. Here it's a square root of 4. This side here is the length of square root of 1.41. This is simply the square root of 1.4. So this triangle again is a little bit bigger. So now what we're going to do is go back to our diagram and just see what the implications are in relation to applying this information to that diagram. Okay, so here we are back with the dodecagon, and what I'm going to do now is simply draw the 30-degree line in relation to this one. It's going to be a little bit exaggerated, but basically that line is going along here just beneath that line like this. And of course the 60-degree line is going to be doing the same thing on the other side, something like that. And the reason I do that is just to point out the fact that this line here, the section of dodecagon with the length of 0.5 root 2, is floating between the 30 and 60-degree lines. So that's the only point I really want to make right there. What I'm going to do now is show you a blown up version of this square here, so we can really look at the precise relationship between the 30-degree line and this line that is the slope of the dodecagon. Okay, so here is a larger blown up version of that same 1 by 1 square, and it's a great example of the base 12 version of the 1 by 1 square, where we have 12 squares by 12 squares, and then inside each of those squares it's a 12 by 12 smaller squares. So what we're doing is looking at the slope of the 30-degree line where it intersects the 1 on the x-axis. So here we have, first of all, the point of the dodecagon with the coordinates of 1 and 0.7. And then we have the point where the 30-degree line is crossing the 1, and that has the coordinates of 1 and the square root of 0.4. And here I've just defined the square root of 0.4 as 0.6b17b27. Of course, that number continues being an irrational number. And so we can see how close that is, the 0.6b1 to 0.7. Again, a base 12 number with the b in there. So we really are in the very last top square. We've gone, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, a, b, and then 0.1, and so on. So you can see what the relationship is there, again, very precisely between the 30-degree line and the slope of the dodecagon line. So now what we're going to do is we're going to look at the growth pattern of the dodecagon, the dimensions of each ring as they progress, and we're going to go to the 4th ring of the dodecagon, and that's going to become the first ring of our diagram for generating all 360 degrees. Just reminding you, that's the intent of this video, is to show you how to create a diagram using this geometric pattern that will eventually result in dividing the circle up into 360 equal portions. Okay, so here we go. Okay, so here we are again with the dodecagon diagram. We've got 4 rings. So what I'm going to do now is go over the lengths of the actual perimeter of the dodecagon, and also the lengths here of this 45-degree line where it intersects the dodecagon on this section right here. So we already know that this distance here is 0.5 root 2. So what we want to do is calculate the entire perimeter. So we're going to multiply 0.5 root 2 by, starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, a, b, 10. So 0.5 root 2 times 10 equals 5 root 2. So that's the total distance of that perimeter. Now we're going to look at the length of this line here from the 0, 0 to that point right there where it intersects the dodecagon. So I can just tell you right now that length is 0.96 root 2. So 0.96 root 2. So we're going to multiply that length by 2 to get the total length of that line inside the dodecagon. So 0.96 root 2 times 2 results in the length of 1.7 root 2. So now what we're going to do is just go over the dimensions of the second dodecagon, the third, and the fourth in relation to these numbers or those lengths. So the second ring, the perimeter is going to be 2 times 5 root 2, and then it's going to be 2 times 1.7 root 2, and then the next ring is going to be 3 times 5 root 2 and 3 times 1.7 root 2, and then the fourth ring is going to be 4 times 5 root 2 and 4 times 1.7 root 2. So again, these are all base 12 calculations. So 2 times 5 is a root 2, and 2 times 1.7 results in 3.2 root 2. 3 times 5 is going to be 13 root 2, and then 3 times 1.7 is 4.9 root 2, and 4 times 5 in base 12 is 18, again, root 2, and 4 times 1.7 is 6.4 root 2. Okay, so again, those are the dimensions of each of these dodecagons, and now we're at the fourth ring. So now what we're going to do is simply divide the perimeter by, I'm going to call it the diameter of the dodecagon, and just see what that works out to, again, as we divide this length into the perimeter. And we're going to do that for each ring. So I'm just going to write that out quickly, and then we'll do the math on that. Okay, so here we have those calculations. So just going to go over them quickly. We're dividing 5 root 2 by 1.7 root 2. And I just realized I didn't write the root 2 here, but these are all, again, same units as here, square root of 2. So 5 divided by 1.7, it goes 3 times. So 3 times 1.7 is 4.9. So we have a remainder of 0.3 root 2. And we're just going to leave it like that and then go to the next ring. We're dividing a by 3.2. So 3 times 3.2 is 9.6. We have a remainder of 0.6 root 2. 3 times 4.9 is 12.3 from 13 is 0.9 root 2. And then the last equation is 18 root 2 divided by 6.4 root 2. And so 3 times 6.4 is 17. So we have a remainder of 1 root 2. Okay, so we're just going to keep that in mind. This is the main equation here that we're looking at. I just wanted to show you how it grows in terms of the consecutive dodecagons. And now what we're going to do is like a physical interpretation of this division of the diameter of the dodecagon into its perimeter. So what I'm going to do is draw some circles on this 45-degree line. And I'm going to draw some circles like this, just all touching each other. 1, 2, 3, and you have to imagine we're going to do all 8. I'm going to leave all this writing on here now. So we have 8 circles, and each of these circles has the diameter of 0.96 root 2, right? The distance between these different sections of dodecagon. So what we're doing now is dividing that diameter into the perimeter. So we have 8 circles, and they're going into this dodecagon that has 12 sides. So we know that 8 is going to go 3 times. So 8 times 3 is 24. So that means that each of these sections is going to get 2 of these circles. So what I'm going to do now is basically erase these circles so they're not in a way, those 2, and I'm going to redraw them on this section of dodecagon. So I want to center them on this line here. So what I'm going to do is, starting in the center, I'm going to count over 0.5. 1, 2, 3, 4, 0.5 there. And same in the other direction, 0.1, 2, 3, 4, 5. And then centered on that point, I'm going to draw this circle. And so it's going to end up looking something like that. And this circle here is going to end up looking something like that. So this circle has a diameter, again, of 0.96 root 2. So its radius is going to be 0.96 root 2 divided by 2. And that results in 0.49 root 2. So again, I counted, we know that this line here is made up of 4 times 0.5, right? So we have 1.5, and so this is 0.49. So 0.5 subtracting 0.5 root 2, subtracting 0.49 root 2 results in 0.03 root 2. So that is the space here between the edge of that circle, or the circumference of this small circle, and the end and the line of the dodecagon. And we also have that same 0.03 gap on this side between this line here and the circumference of that small circle. And then again, we have that same 0.03 on the other side, and then right down here on this side. So we have a total sort of gaps between these two circles of 4 times 0.03 root 2, and that results in the answer of 0.1 root 2. And then what we're going to be doing is repeating that all the way around this circle. So of course, 10 times 0.1 root 2 equals 1 root 2, and that's the total amount of empty space, so to speak, that we had left over when we took that, what I'm going to call sort of the solid diameter, and divided it into the perimeter of the dodecagon. So that's what this looks like so far. I'm going to put my whiteboard behind just so you can see that clearly. Okay, so that's what all of that looks like there. And again, we have a line going through here that is the length of 1.8 root 2. And then again, that times 10 equals 18. Again, these are all, root 2, root 2, root 2. We're going to be working completely in units of square root of 2 as we build the diagram for 360 degrees. And these are the units that we're going to be working in. So what I'm going to do now is show you how we take all this information, this geometry here that we just created, and how do we move it down to this section of the dodecagon so that it's exactly in proportion. The relationship of these circles, these two circles, to the 45-degree line is exactly the same as the 15-degree line here. So what I'm going to do now is just take a quick detour, and we're going to go over the geometry of determining where that 15-degree line is, just to make sure that we're all on the same page. We know that it's easy to create, and then we're going to use that 15-degree line to, I'm going to show you how we move that information down to this section of the drawing. Okay, so here are the steps that we need to take to divide the circle, get to this point here, into 24 sections of 15-degree sections, or in base 12, I'll be saying into 20 sections of 13-degree sections. Okay, either way, it looks exactly the same. This is the pattern that we're going for. So we could either start with a line and then put our compass on that line and draw a circle, generating 2 points, or we could start simply by drawing a line or drawing a circle, putting our compass on the edge and drawing another circle that would generate 2 points. But either way, we're going to continue putting our compass on the points where the circles are crossing each other or intersecting, and then drawing more circles until we get to this pattern here, where we can draw our x-axis, and then where these 2 points are intersecting, where those points have been created, we can connect them and get our y-axis, and continue drawing circles with that being the center, and then we get more circles with more crossing points and drawing more circles until we get to this pattern. And then from here we can start connecting the points, and this is how we get to this point here. And you can see we can also connect those points in such a way that we begin creating a grid if we wanted to actually draw our entire XY coordinate plane using just compass and a straight edge. Okay, so this is where we want to get to. So I've just shown you how basically very easily we can divide that beginning circle into 20, speaking in base 12, 13-degree sections. We're going to be using this line now to move the information, like I said, from the top of that diagram into the lower section. So here's how you do it. Okay, so here we are back with the dodecagon, and what we're going to do first is draw a circle with the radius of this point here, which is 4 times 0.96 root 2. So 4 times 0.96 root 2 is 3.2 root 2. So 3.2 squared is a.04, so the square root of a.04 times square root of 2 is the square root of 18.08. So we're going to draw a circle that looks something like this. Okay, and so here is our 15-degree line or 13-degree line in base 12. And so this circle obviously is crossing this 15-degree line right here. And here's the 45-degree line crossing that same circle. So now what we're going to do is we're going to go over to the point where that, as you can see, I've taken those circles off, but we're going to go to the center point of one of those circles. We're going to count over 0.5, 1, 2, 3, 4, 0.5 right there. And we're going to look at that as a right angle triangle like this, something like this. And so we're going to calculate the length of this radius. We're going to draw basically another circle with this radius here. So in order to calculate that, we're going to do, again, a squared plus b squared equals c squared, ABC. This is a right angle, so it's going to be the square root of 18.08 plus, I'm going to write it underneath, the square root of 0.42. Again, that's 0.5. This length here is 0.5 root 2, so you square 0.5 multiplied by square root of 2, we get square root of 0.42. So we add those together, we get the square root of 18.4a. So that's the radius of the second circle that we're about to draw, just like this. It's sitting on the outside of the first circle. So we have these two circles. And again, both of them are crossing the 15-degree line down here, obviously. So then what we do is we set our compass to that length of 0.5 root 2, and we take it from here, and we go down and we place it on this point, and we make a mark on the outer circle, the radius of 18.4, or the square root of 18.4. Make a mark on that side, and then the same on this side. And then we reset it so that the radius is 0.49 root 2, so make it a bit smaller. Same as these circles. I'm going to draw them in now. One's going to be right there, one's going to be right there, roughly. So then on that mark, we put the compass down, and we draw another circle like that, and then another circle like that with the center of the points we just drew. And so those circles are sitting also on the outer circle with the radius of the square root of 18.4a. And so now their relationship to the 15-degree line is exactly the same as the relationship of these circles to the 45-degree line. So now what we've done is we've created some more points here. And so what's interesting to see, we've got these kind of what I'm going to call sort of like tunnel lines, where each of these degree lines has sort of some width to it, or a gap on the other side. So the total distance of that is 2 times 0.03 root 2, which is 0.06 root 2. So of course we can connect those two lines like that. That's exactly the same as these two lines here. So now what we notice is that we can also simply draw a line between these two circles right here like that. And basically this, I haven't drawn it so well, but this gap here is going to turn out to be exactly the same, which is going to be 0.06 root 2. So that the reason that works out so well, remember we had our 30-degree line in here, so the relationship of this dodecagon line and these circles to the 30 and 60-degree line is going to be exactly the same again here as it is to there. There's a bit of a gap between, and so when we redraw or we remeasure this distance here, we have the distance of the radius of that circle, and then there's going to be the same gap. And it just works out because of the quality of the dodecagon, how it's a continued line that's all connected, and these gaps here are these lines, how they connect. They don't swing past each other. So if you sort of think of this line as a line that's sort of swinging over, nothing's actually moving. We're just drawing a line between these 2 points, and it simply works out. It's kind of forced to be the exact same distance all the way around. So what I'm going to do now is show you a precise version of this diagram, what it looks like when all of these circles have been drawn and everything is in proportion. And then you can see what this looks like. This again is the first ring of the entire diagram that's going to be used to generate all 360 degrees. All right, so here's that same diagram but drawn to the correct proportions. You can see I've included this pattern on the inside just to indicate that that's the initial starting place for this diagram, and that's how we get the initial division of the circle into 24 sections, each of these sections being a 15-degree section. And I've shown you how we found the points for these small circles, and then you can see here now I've also drawn these larger circles. So this circle is anchored on the actual dodecagon. So the radius of this circle is 2 times 0.5 root 2, which equals out to 0.8 root 2. So you remember the initial dodecagon was one length of 0.5 root 2, and then 2 times 0.5 root 2, 3 times, and then 4 times is the total length. So half of that is 2 times 0.5 root 2. So this section here, this circle with this radius, is the unit that we're going to be working with. So here we have these circles sitting on, or sort of within a 30-degree section of the diagram. So what we're going to be doing is creating more rings, and as we go out, we're going to be adding one more of these circles in each ring. So the next ring is going to have 2 of these circles in it, and the ring after that is going to have 3 circles, and we're going to keep adding rings until we get 30 rings. So the 30th ring is going to have 30 of these circles in the 30-degree section, and each of these circles is going to have take up the space of 1 degree. So that's going to be the finished result, the finished product of this diagram is going to be a circle that has 360 of these circles in its circumference. Okay, so that's where we're going to be going, but before we get to that point, what I want to do now is calculate the angle that's been created within these smaller circles. We can see that, when we join these 2 lines together, and then we put a line from this point to this circle here, there's an angle here, and now we want to figure out just what that angle is. So we know that there's a formula for that. In base 10, it is n minus 2 times 180 divided by n, where n is the number of sides in this polygon that we've created. So we know we've got 12 of these, and there's basically 2 sides, 2 edges in each section. So this is a polygon with 24 sides. So n in this section is going to be 24, and the base 12 version of this calculation is basically the same thing, n minus 2, but we're going to be multiplying by 130 instead of 180. So what I'm going to do now is quickly do those calculations and show you what the results are. Okay, and here are those calculations. So you can see the base 10 version. When we go through, we get to the answer of 165 degrees. So in base 12, when we do n minus 2, n is going to be 20 here. So 20 minus 2 is 1a multiplied by 130 equals 2360 divided by 20 equals 119 degrees. So again, it's the same amount of degrees, just the base 12 version of this whole number. That's what it looks like. That's the answer for that particular ring. So that's all the information that's basically encoded within that first ring. So I think I mentioned at the beginning of this video that I'm an artist. I like to build things. So what I've done is actually built this diagram. I've gone and created a the next rings in this series. I'm going to show you a picture of that right now. Here's what it looks like. So you can see if you count these rings, there are 15 rings in this construction. So this is halfway to the completed version, but it's enough to show you how this works, how all the degree lines are created. What I'm going to do now is bring that construction into my living room. We're going to go over it section by section. Basically, it's made up of 5 sheets of plywood. So we're going to look at them one at a time and just go over the process of creating the entire diagram. The image I was just showing you, the first circle, is the one that you see down there on the bottom left, the complete circle. And now we're just going to go over the process of creating each additional ring. Okay, and so here is the first panel that we'll be looking at. This is the one from the bottom left of the construction. So you can see this is the circle that we were just looking at. And here this is the only spot where I've drawn the larger circles around the smaller pairs of circles. So we'll just kind of pick up where we left off. There's the formula for figuring out the angles inside of each of these small circles. And again, 119 is the base 12 version, 165 is the base 10. So for this diagram, I've basically gone all in on the duodecimal element. All of the numbers are duodecimal in black, and I've included some of the base 10 versions in red. So over here, I've just sort of done a comparison or a conversion from the base 10, 15, 30, 45 degrees into the base 12 of 13, 26, 39. You can see that 360 degrees in base 12 is 260 degrees. And then here is basically a list of the sides of the polygons that are created in each ring. So we already plugged in the number 20 for the first n in the first ring. So the next ring is going to be 40 sides and then 60 and 80. And you can see how sort of easily the base 12 side works, while the base 10 is a little bit different. 24, 48, 72 is not quite as sort of even looking. Okay, so just going over this, what I want to do now is go over the process that we use to create each ring. So we're always going to be starting with the 45 degree. We're again working in units of square root of 2. And we're always going to be working in this sections of 3.2 root 2. So the next ring, we're going to go to 6.4 root 2, right? So we go 1, 2, 3, 4, 5, 6.4. We have a specific lattice point. We put our compass down there and we draw that ring. And then we're going to add 0.5 root 2. So that's the square root of 0.42. And then we're going to get the square root of 68.6a as the radius of our second ring. And we draw that ring also. So we're always, the first step is always going to be drawing those two rings, or finding their position and then drawing them and then working off them to create the new points for the, basically a finer division of that particular ring. So in this second ring, we already got all the degree lines that we need. So I have coined a phrase called twinning the degree line, which relates to how we find these points where we put our compass down on the point where our degree line is crossing the inner ring, and we set it to 0.5 root 2. Then we make a mark on the outer ring. Then we readjust our compass to 0.49 root 2, and we draw these circles. So again, these circles all have the radius of 0.49 root 2. So we're always going to be able to twin the x-axis and create the position for the ring that's sitting, the little circle that sits on top of the x-axis. And we're always going to be able to twin, the 15 degree line, 30 degree line, 40 degree line, however that pattern works out. So you can see the pattern for the 7.5. So we did create in the first ring, we've divided that ring up into sections of 7.5 degrees by creating these smaller rings on either side of the degree line. We divided the 15 degree line in half, basically. So we have this, and there's a pattern here for this particular degree line where here the line is going through, and we draw our circle right on top of it. And then here it sort of splits two of the smaller circles. And then on the next ring, you can see we're drawing our circle right on top of it on the outer ring. And then the next one, again, it's going through, and that's the pattern that continues for that particular degree line. So the second ring is being divided into sections of half of 7.6. So this degree line here is 3.9. I don't know if you can quite see, but this is the second ring. So in the fourth ring, that 3.9 shows up again. And there's also patterns within this series. So here we have the third ring. So we do the same thing. We're going to go up to 45, draw the first ring with the radius of 3 times 3.2, which is 9.6, which works out to square root of 130.6. Then we're going to add 0.5 root 2, square root of 0.42, we get 130.A2 for the second ring. And that's something that's interesting to note as each ring progresses, because we're always adding the same amount, the same length in our very elongating Pythagorean theorem triangle. Because that section is always the same, but the circles are getting bigger, the gap between the inner ring and the outer ring is getting narrower and narrower. And actually that's this number here. Here the gap between those two rings is 0.0569. That's where we can measure it on the x-axis. Here it's 0.0296, goes on. Here it's 0.01 and so on. So that number gets, again, narrower and narrower or smaller as the rings progress. Okay, so this particular ring is interesting because, again, half of 5 is 2.6, so we're dividing this particular ring into sections of 2.6 degrees. And so it's just interesting to note, again, because we're in base 12, we're dividing the entire ring into sections of 2.6, and then the 30-degree section in base 12 is 26 degrees, and the entire circle is 260 degrees. So we can see in base 12, we have this ability to just move the decimal place over 2.6, 26, 260, while in base 10, it would be half of 5 is 2.5. We have 30 degrees and then 360 degrees. So it just doesn't line up the same way as it does in base 12. Okay, I'm just going to adjust the camera a little bit here. I had to back up to make sure everything was in, but there's the next two rings. And again, like I say, the 3.9 is showing up here, the second ring, then the fourth ring. And we're going to see, here's the third ring for the 5 degree. And then on the sixth ring, which is going to be the next panel, we'll be working in sections of 5 degrees again. So here we're going to be dividing the inner ring up into sections of half of 3.9, which I think is 1.A6, I think. We're at 128.3 degrees or 176.25 in base 10. So again, of course, as the circle gets bigger, the angle inside these smaller circles is getting wider. We use the same approach or style of first drawing the inner ring, then the outer ring. We are able to twin the x-axis and get this point here. We're able to twin the 7.5 degree angle and get those points there. And so it's, again, we can easily find all of those circles just by working off of the degree lines that we had before. And I think you can still see easily enough the next ring. So again, here we're going to be twinning the x-axis to create that point there. And then we can draw our 7.5 degree circle there. And so we've got these 2 points. So, but then to create the middle one, we're basically going to find the midpoint. So we can easily find the midpoint by using our compass, placing it, basically the distance between these 2 points, and then finding the midpoint between them by drawing circles and crossing them over. And then we can find that midpoint here, which is going to be this point there. So that's going to be our, half of 3 is 1.6, so 4.6 degrees. And then we can find, the midpoint between there and there to get our 3 degrees and our 6 degrees. So each ring, we can find all of the various degree lines simply by finding the midpoints between either the circles themselves or the degree lines that are already introduced. And sometimes it's quite a big gap. Here we're able to keep, reusing earlier degree lines, but sometimes like on the 7 or the 11, it's all new. We only have our sort of x-axis and our 15 or 30 degree lines, 7.5. Those ones are consistent. We're going to get to that in a little bit. I just want to go over, basically, it's not so hard to generate new degree lines on each ring as we progress, just slowly finding the midpoints between the degree lines that we've already established. Okay, so now I'm going to go to the next panel. All right, so here's the next panel in the series, and this is the 6th ring, and you can see, as I mentioned before, here's the 5 degrees again. So it shows up here, and then the 7th, 8th, 9th ring, again, we're doing 5, and then 9, so the AB 10th ring is also over there going to be working in groups of 5. So here we're dividing the 5 up into quarters, so that this ring is divided into sections of 1.3 degrees. So here's our 7th ring. As I was saying, here we have the 7.5 degree line already established, and again we can twin our x-axis, so we would be able to find the position for this circle, and we've got the position for this circle, so then we can find the midpoint between these circles would be here, and then once we've established that point, we can twin this degree line to find the positions for these 2 circles, and we've created these new degree lines as well. So it's easy, again, to just use a combination of always finding midpoints between either the circles or the degree lines that already exist. So this is the 8th, 9th, we just continue. You can see the angles inside, these getting smaller, but the progression, the difference between these angles gets smaller and smaller as well. You know, 129.6 degrees, 129.8, here a repeating decimal, 128.16, 128.4, etc. Here is the 10th ring. So you can see I've color coded them also a little bit. So every 3rd ring is green color. Every 5th and 10th is the orange. So we're just continuing along. I'm feeling a little bit self-conscious about how long the video is. I feel like you're getting the idea of how this all works. So what I'm going to do now is go to the next panel right away, and we're going to look at the 15th ring, where all of the even numbers start to show up, and we're getting close to the completed diagram. Okay, so here's the last panel in the series. So we're at the 15th ring now, and you can see here the color-coded degree lines are showing up. We have the x-axis, and then here's the 3 degree line that was established earlier in orange, the 5 in green, and then of course from the 3 we get the 6, the 9, the 10 in base 12, and then 15, and then the green is like 5, 10, or I got these 2 symbols here. They're called dec and L, which are alternates to the A and B. I just put them there, go into that later. So 10, 11, 12, 13, 14, 15. So we can twin all the lines that we can, and then the 15 degree line and the 10 here. So then we can find the midpoint between to establish that circle, and same process as we've been doing all the way along. So now we have all of the even degree lines established on this 15 degree ring. So again, what we're looking for the finished diagram is to go to the 30th ring and then have each of these larger circles be 1 degree section. Right now, basically they are 2 degree sections. So again, that element of doubling the ring length from the center kind of halves or doubles the size of the degree lines, or the space between them. So as far as the angle inside of each of these little circles, we are now in base 12, it's 1, 2B. You can see that there, or in base 10, that's 179 degrees. So again, it's working out really evenly, and we're 1 degree shy of a straight up and down 180 degree flat line. So obviously, as we progress with these rings, the angle or the slope or the edge or the circumference of the circle is becoming flatter and flatter, or more upright. So we're going to explore that idea a little bit more in a minute. But what I want to do now is go into the geometry, or show you what it looks like on the 30th ring. So I'm going to put this away, and I'm just going to draw that out for you, because this is as far as this diagram goes, and we're going to look at the details or the elements or the numbers involved in the 30th ring of this diagram. So I'll do that for you right now. All right, so the first thing I want to do is calculate the interior angle inside those smaller rings on the 30th ring. So again, in base 12, that's the 26th ring, so I've included both versions of that calculation. We'll start in base 10. So our n is going to be the 30th ring times 24, because the first ring had 24 sides. So we're just making that calculation, and we get 720 sides to the polygon that's created by the geometry of the 30th ring and the pattern that we've created so far. So 720 minus 2 is 718, multiplied by 180 is 129,240, divided by 720, we get 179.5. That's the amount of degrees, the angle inside the smaller circles at the 30th ring. So in base 12, what that works out to is, again, 26 times 20, same numbers, we get 500 in base 12, minus 2 is 4BA, multiplied by 130 is 62,960, divide that by 500, we get 12B.6. Again, same number, but just the base 12 version. Basically now we are half a degree from 180 degrees, or 130 in base 12. So that's the degree inside the circles. Now we're going to look at just what the geometry looks like, the positioning of those circles, and what that looks like inside each circle. Okay, so here's the last ring of the circle where I've just drawn it freehand. So the radius of the final circle that we're working on is 7b root 2. So at the ring before that we're just looking at, the 15th ring, had the radius of 3b.6 root 2, so we're just multiplying that by 2, we get 7b root 2, which is the same as taking 3.2 root 2, which is the gap between each ring, multiplying that by 26 in base 12, and again we get 7b root 2 as the answer to that equation. So that's the radius of the final circle. This is what it looks like, and you can see now, at the 15th ring, we had the distance between the diameter of these circles was 1 degree. So, the midpoint of that circle was half of that. So we were working with a circle that had been divided into half degree sections, 0.6. So now we're, again, halving that. We're working with the line that's being divided into quarter degree sections, or 0.3 degree sections. You can see 0.3, 0.6, 0.9. Here's our 1 degree. So as these degree lines are coming out and intersecting with the circle with the radius of 7b root 2, we're able to put our compass on that point and go over our process of twinning the degree lines. So we're just creating these new points. Here's the 1 degree, 2 degree, 3 degree lines. That's what that looks like on the 30th ring of this diagram. Okay, so I'm going to leave it there as far as the sort of physical diagram and looking at its various components and sharing how to actually construct the diagram. I think I've given you a good overview of the entire diagram that generates 360 degrees. This is what the 30th ring looks like, and we do indeed have all 360 degrees encapsulated in that circle. So what that has done, we've generated on the circumference, I'm going to talk in base 10, 720 points on the circle, 500 in base 12. Again, all of these spaces between the points has been defined. We've got lines going through, and again, the angle inside these little circles is 179.5, or 12b.6 degrees. Okay. So now what I want to do to get closer to wrapping all this up is engage in something of a thought experiment. I've run out of things to draw. I don't want to do any more equations, but I just want to entertain the idea of what happens next. We've got this diagram. We've created basically a perfect circle. We're placing points on the circle that are all evenly distanced from each other. We're able to mark their degrees, and we can keep dividing. We're working on the coordinate plane, so everything is very well anchored. We're using lattice points to determine the exact positioning of these rings. The gap between the two rings now is incredibly close, and we can, as we continue, we're just getting more and more precise and more fine-tuning all those points as the circle gets larger and larger. So what happens as the circle gets larger and larger? What goes on the circumference? So let's just imagine that this point here, we're only, basically the radius of this circle is only about 30 feet long. What if we were to imagine a circle that, is a mile in radius, or even go bigger, let's go really extreme, have the radius the same as the radius of the Earth, really big, or even go farther, the distance from the Earth to the moon, a really big circle, or think about the distance from the sun to the Earth, or let's even go bigger, a circle with the same scale that is the same size as our entire galaxy. What's the circumference of the circle? What is the geometry of the circumference going to look like at that point? So what I've done is created some little cardboard cutouts of these circles just to show again the precise scale of the relationship between these smaller circles and this gap between them. Again, these small circles have the diameter of 0.96 root 2, or the radius of 0.49 root 2, and the gap between them is 0.06 root 2. So again, we're working in units of square root of 2. What I'm going to point out is that there comes a point when these circles, the circles themselves, are going to be exactly above each other in a straight line. The distance, or these circles here, their distance, we'll be able to draw a line exactly straight, perfectly straight between them, and that all the kind of action that's happening in the curve of the circle is taking place within this 0.06 root 2 gap between them, where we have these tiny segments, again, look at it this way, these tiny segments of angle, where the angle is going to be something in base 10, 179.9999999 degrees will be the angle in there. And really it's empty, so the empty space there where that is happening. Okay, so what's going on there is, again, I've got this circle here, I'm sort of turning it sideways, and we're looking at that line there, and yet we also are able to look at that line, that straight line, as a series of these circles with the space between them, just as we have here. So what's happened, if you remember, we still have our diameter, and our diameter is just the total amount of these small circles. Nothing's been added. We're not adding any extra material to the circumference. We've simply taken the diameter, divided it 3 times into the circumference, and everything that's left over is been evenly distributed within these little gaps between the circles. So we have a solid line as our diameter, and we have a broken up line in our circumference. Now, of course, I've gone to the example of making a really big circle the size of our solar system. We could reverse that process and acknowledge that what we've actually done is taken a sort of normal sized circle, and we've really looked deep into it. We've divided up. We've gone into the very, very small. And again, we've created a geometric model where we have some empty space, or our line isn't a solid line, but it's a line that has some empty space evenly distributed all the way through it. And so now I want to talk about applied math versus pure math, and how this would apply to our actual knowledge of the structure of the universe. Because we know that ultimately when we look at something that's built in the universe, let's say, for an example, this ruler, we know that although this appears to be a solid line, a solid length of material, if we start to look more closely at what it's made of, we know that it's made up of plastic molecules. Those molecules are made up of atoms. Atoms are made up of protons, neutrons, and electrons. And when we get down to the quantum realm, there's actually a lot of empty space inside or between all those components. So we know that ultimately this ruler isn't just a solid ruler, but there's a lot of empty space distributed evenly throughout the length of that straight solid line. So now I want to bring up, I don't know if it's like the elephant in the room at this point, or what if you've already caught on to this, but what about pi? We're talking about the diameter of the circle, we're talking about the circumference, we're dividing the diameter into this circumference, and we found a way to do it where we are breaking up that solid line into a line that has evenly distributed empty space. Now, our current version of pi, when I go to Wikipedia and I take a look at the illustration that they have there, it's a circle. They make a mark on its circumference, or a wheel that rolls along the number line. It marks off one complete revolution, and that distance is 3.14, etc. So our current version of pi is a solid line, and then at the end it's a fixed point where it stops, and yet the numbers that define it continue on. And I just saw an article recently where they've redone or gone farther, and there's literally billions and trillions of decimal places that we've calculated for this number. So we have, again, a solid line with, I'm going to call it an empty space at the end, where we keep adding more numbers, and yet it's also a fixed point. So we're kind of putting numbers into an empty space at the end of the line. So what I'm suggesting is that this model is a more accurate model of what the universe is actually like when we go deep into the physicality of our universe, that empty space isn't just at the end of one length of line, but it's actually dispersed all the way through. So this explains, I'm hoping, the paradox that seems to exist between a solid line with fixed ends and the ability of irrational numbers to seemingly go on forever. So this also applies to something like the square root of 2, where instead of having a solid line with kind of a gap at the end where we can't quite figure out where the line ends, although we know that it is the lattice points that are on either side of the right angle, 1, 1, square root of 2. So what I'm going to do now is go back to the beginning of this presentation where I introduced you to this dodecagon that's built in here. Remember, the length or the diameter of this circle is one section of the dodecagon. We're still using the geometry of the dodecagon. In this example, we just keep dividing and dividing. We already have a fixed circumference. We know the precise length of our dodecagon, and what we've been doing is using that as a model to base the entire structure of this circle upon. So all of this geometry already existed in base 12. It's simply that nobody's taken the time to really look deeply at it because it's in base 12. There's been this prevalent view that really base 12 isn't worth exploring, so that's why nobody's really looked at it as far as I can tell. What happens if we go a little bit deeper or follow through with that equation that I did at the very beginning, where I was actually dividing the diameter of the circle into the circumference, or at that point it was the perimeter of the dodecagon. So we're going to do that now. We're going to finish up this entire presentation by actually doing the equation where we're taking those two values, and I'm going to show you what the result of that equation is. Okay, so here we are back with that original diagram that I showed you, or I introduced you to the dodecagon at first. So what we're going to do is use the numbers that define this very first inner ring of the dodecagon, although of course we could use any combination of the ring and the corresponding diameter. So if you remember, this first length here is 0.5 root 2. So 0.5 root 2, I'm just going to write it up here, and we're multiplying that by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, 10. So multiplied by 10 results in a perimeter of 5 root 2 for the perimeter of that first dodecagon. And then this length here was 0.96 root 2, 0.96 root 2. And of course, we're multiplying that by 2, 1, 2, to give us the complete diameter of the dodecagon, which results in the length of 1.7 root 2. So now we have the option of doing this equation in two ways. We can either cancel the square root of 2 and just do it as a straight dividing 1.7 into 5. So that's going to look like this, 1.7 into 5. And I think if I remember correctly, move the decimal place over, so it's going to be basically 17 into 50. Or we could convert those numbers into complete square roots and then do the equation as square roots. In that case, what we would be doing think you remember that 5 root 2 converts into the square root of 42. I'm just going to write that down here. Square root of 42. And then 1.7 squared equals 2.61. So the square root of 2.61 multiplied by the square root of 2 results in the answer of square root of 5.02. So we're going to be dividing 5.02 into the square root of 42. So what I'm going to do is both of these equations for you. I'm going to start with this one here. So 17 into 50 now is going to go 3 times. So 3 times 17 is 49. We have a remainder of 3 because, again, it's a duodecimal equation. So here we go. So we're going to bring down a 0. So that's going to be 1 time. 1 times 17 is 17. The remainder is 15. I got it written down here just to remind myself. I'm going to bring down another 0. That's going to be A. So A times 17 is 13A. 13A has a remainder of 12, right? A, B, 10, carry 3, 4, 5. We're going to bring down another 0, 120. So that's going to be 8. 8 times 17 is 108. 108. So we subtract that from 120, we get 14. 14. So we're going to bring down another 0. 14 is going to be A again. That was 13A. So the remainder is 2. There we go with the 2. So we're going to bring down another 0. 20. So 17 goes into 20 once. 1 times 17 is 17. And the remainder is 5. So we bring down a 0. And we're back to the 5 that we started with. So the next one's going to be 3. And this is now a repeating decimal. 3.1A8A1, 31A8A1, and that just keeps repeating like that. So that's the answer that we get when we knock off the square root of 2 units and we just do it as a straight long division question. Okay, I'm just going to leave it at that. Now I'm going to do the same thing with this equation. We're going to divide square root of 5.02 into the square root of 42. I guess the same thing. We're going to move the decimal place, and it's going to be the square root of 502 into the square root of 4200. I'm just going to clear off the board and calibrate everything, and then I'm going to present the answer to that equation for you. Okay, so I have to admit I'm having a little bit of trouble with this final portion of the video. I don't really want to spend the rest of it doing this equation, so what I've done is I've just taped up the math here on this little forlorn piece of graph paper behind me. I'll kind of do a quick pan over it at the end. But what I want to do is talk about the result quickly. I do feel like I've accomplished the goal or the sort of mission of this video, which was to show or teach how to construct a diagram that generates all 360 degrees using base 12 geometry. I've introduced you to the dodecagon, the pattern that we've missed in base 10. I've explained why we missed it and what the difference is between base 10 and base 12. So as far as all that goes, I feel like I've presented that information in as clear and concise a way as possible. So this final aspect, this was the surprise that I had for you, that the base 12 version of pi, I do believe this is the base 12 version of pi, is different, has different qualities than the base 10 version. And so the question is it right? Is this really true? What are the implications? Or perhaps it isn't right, and if not, why not? So the number that I've calculated is a square root. It begins with 9, so it's a square root of 9.B8017191, and then it continues for 96 digits. So that's a 96 in base 12, which in base 10 is 114, I believe. So that's interesting that the 96 relates to the 0.96, that unit that we've been working with throughout this video. So again, what happens at the very end, it's a 0 and then it repeats. It starts again 9.880171, etc. But I don't think it's necessary to repeat the number. I think that length of just over 100 digits is the concise finished version of pi. And in relation to pi and the Planck length, talking about physics and applied mathematics, I believe that's the correct version of pi, which leads us down to the Planck length and then basically stops. And there's still that empty space around the number that I was talking about earlier, which then enables us to continue if we want to. But really, that's the defining pi that fits with our physics of the universe that we've got to at this point. So I think I'm just going to leave it there. I've said a lot already, food for thought. I am going to be exploring these ideas more on my YouTube channel. Again, dual decimal division. I'm in the process of, getting an Instagram account going and all this kind of stuff, getting the word out, so to speak, exploring this more. There is more to this. There's more geometry. I'm basically ahead of this presentation in terms of my own research, and you'll be hearing more from me in the future, hopefully. So I just want to thank you for setting up this contest that enables me to submit this video. I hope you've enjoyed it, and like I say, food for thought. So thank you for taking the time to watch this. And so here is the the base 12 version of pi, what I believe, in my opinion, is the one. And I really feel that the physics of the universe has more to offer if we use base 12 math to explore, or maybe say that differently. This version of pi and the geometry that goes with it is the math that will lead us into new discoveries within the realm of quantum physics. Okay, so that's how I'm going to wrap it up. Thanks again for watching. Bye for now.